Okay, we got one more to go here, which is equilibrium. So we're going to talk about equilibrium in this chapter. Talk a little bit about writing equilibrium constants, doing a little bit of calculations, and officially the Chatleir's principle. So equilibrium really involves a specific type of reaction, and that type of reaction is really a reversible reaction. And these reversible reactions typically will have obviously these arrows that head in both directions. And that means that there's basically kind of two directions that occur in an equilibrium reaction. There's kind of the traditional reactants to product sort of direction, which is referred to as the forward direction. And in these type of reactions, what will happen is at some point, some of those products will actually recombine and head back the other way. And when that occurs, we get a reaction happening in what is referred to as the reverse direction. And at some point, this reaction will reach what's referred to as chemical equilibrium. And sometimes when people think about equilibrium, they have maybe a misconception about what that means, hence the word equals in there. So sometimes they think that means that you have equal amounts of reactants and products when it reaches equilibrium. And that's really not what it means. What it does mean, as we'll talk about a little bit more as we go through this chapter, it's really the rate of the forward direction will equal the rate of the reverse direction. So what that means is just as quick as it sort of breaks apart into products, those products will basically recombine and head back the other way and make your reactants. As we'll talk about, basically what that will do is it pretty much will lock everybody into place in terms of where they're at, in terms of their concentrations, or even if it's pressures, if we're talking about gases, for example. And they really won't change because just as quick as it kind of goes to the products, it's just going to come back the other way. So it just sort of locks everybody into place as it keeps going back and forth, basically at the same rate. So let's talk a little bit about reactions and sort of, again, how it occurs. And sometimes referred to as the collision model. And really for a reaction to take place, we're really just going to break apart all the bonds and basically reassemble everybody on the other side. In order for that to happen, there's really kind of two things that is necessary for products to actually be formed. And that is they do need to collide with each other, but they actually do have to kind of hit each other in the right location. So if they kind of hit each other in the wrong location, you really won't get products to form. And the other really important thing is they do have to sort of hit each other with the right amount of energy. So you got to have those two things. They do have to collide in sort of the right location, and they do have to collide with the right amount of energy in order for products really to form. So not all collisions, as I said, will lead to actually product formation. But if you do have those collisions that, again, are in sort of the right location and with the right amount of energy, you will get products to sort of form. And what happens or helps us with rates of reactions and how fast a reaction will occur, a couple of things are really important for that, and that's concentration. So if you increase the concentration, that typically would increase the rate of a reaction because you have a lot more, say, reactants. So they don't have to go search each other out. They can find each other a lot quicker, and that would allow the reaction to take place. Even if you had a lot more products, say their concentrations, it wouldn't take as long for those guys to come together and come back on the reverse direction in a reaction. Opposite would be true as well. Obviously, if you had a lower concentration, remember that concentration or molarity, for example, right, is moles of solute over liters of solution. And really in a reaction, especially sort of a solution, aqueous type environment, it is those solute molecules that basically are what are reacting. So the larger the concentration, the higher the solute guys are floating around in there. Lower the concentration, a lot less of those guys floating around. It's going to take longer for everybody to come together and for that reaction to take place. Temperature as well plays a really important role. If you increase the temperature, typically the rate of the reaction will occur a lot faster, and that's for that energy part of it. So obviously, if you increase the temperature, everybody has a lot more energy, which means that they will be able to, when they do collide, have the sufficient amount of energy basically to make products. And you typically will see the rate of the reaction increase. For example, if you increase it about 10 degrees Celsius, usually you can kind of double the rate of a reaction for a lot of reactions just by simply just bumping up the temperature kind of 10 degrees. The opposite would be true as well. If you have a lower temperature, you're going to have a lot more molecules with less energy, and those molecules are now going to have less energy really to kind of get up and over to the other side to make the products. So the rate of the reaction typically would sort of slow down. So if you threw everybody on ice, you typically will see that reaction rate kind of slow it up. You throw them in some hot water, your test tubes, and you're doing some type of reaction, you kind of would see a sort of increase because of the increased amount of energy that's present. Any questions on that? So that brings us some energy diagrams, which we've talked about, I think, previously when we were doing the energy chapter. But remember, there's kind of two types of energy diagrams when we look at it. And I'll draw them here, I think. And if we look at one, for example, that looks something like this. This is our reactants, this is our products, this is energy. Versus one that looks maybe something like this. Reactants and products in this case. So the guy over here on the left, our reactants are higher in energy than our products. So again, the only way really for the products, the reactants to get down to the products is to release energy. And this is why this is a exothermic diagram. And that's opposite of what we see on the right-hand side. On the right-hand side here, we have reactants lower in energy than products. Only way for them to kind of get up there is to put energy in, and needs to absorb energy. And this would be an endothermic reaction. So as this reaction is taking place, basically all of our reactants are starting to break their bonds, and they're starting to make new bonds. And there's really that hill that they have to climb to get to the other side. And that is really reactants start to sort of the peak of the energy. That again is your activation energy. And that activation energy is that minimum amount of energy that's required for a reaction to take place. It's again that hill of energy that the reactants has to climb to get basically to the other side. For our endothermic reaction here, it would be here, our E of A. So clearly the size of that hill that they have to climb also plays a role in terms of rates of reactions. So obviously the larger the activation energy, the slower the reaction may occur. The smaller the hill they have to climb, much faster that the reaction would occur. Also, because if you have a smaller hill, then you have a greater proportion of molecules that probably have enough energy to get up and over to the other side, rather than a giant hill where there's not as many that can kind of get up and over to the other side. This is also why when you play with the temperature, it affects the rate of the reaction. We increase the temperature, now you're going to have a greater proportion of molecules that do have enough energy to get over that hill to the other side, and that would increase the rate of the reaction. Just like if you lowered the temperature, you would have a much smaller proportion of molecules that now can get up even over a smaller hill. It's going to be a much smaller amount of molecules that have enough energy basically to do that. That the most highest sort of state of energy, that is our transition state, which is up here. And the transition state is a lot of times where we have this sort of intermediate type of compound where it has partially broken bonds, partially made bonds. It's sort of that intermediate before it sort of fully breaks apart and reassembles onto the other side. The other thing that we talked about as well is delta H, right? So delta H helps us understand, which is the enthalpy of a reaction, and that is products minus reactants. So here, if we look at our exothermic sort of diagram, we take the difference between where the products end up and the reactants end up. That's our delta H of a reaction. And in this case, our products are actually lower in energy than our reactants. So when we subtract the two, we end up with a negative value for our delta H value. And over here, where our reactants and our products, again, where our products end up, where our reactants started is our delta H of that reaction, or the enthalpy. And in this case, the products are actually a higher number than the reactants. So larger number minus a smaller number will give us our delta H that is positive in this particular case. So all these factors obviously affect the rate of the reaction, the hill that they have to climb, how many guys have enough energy to kind of do that. Any questions? I'll leave those there. Now, one way that you can sort of speed up a reaction is actually adding a catalyst. And a catalyst is not a reactant, nor is it a product, and it does not get used up in a reaction. So not a reactant, not a product, and does not get used up. It is there in most cases to facilitate the reaction occurring a lot faster, and that may be finding an alternative pathway for that reaction to occur. Sometimes catalysts are just simply metals, which attracts everybody to a central location, and that allows them obviously to be near each other and start the reaction a lot faster than if they were just kind of floating around. If there were gases, for example, having to find each other instead of everybody just sort of coming to a central sort of spot. The way it ultimately does so, as we might have talked about in that energy chapter, is a catalyst will lower this activation energy. So you get this lowering of the activation energy between the catalyzed reaction and the uncatalyzed reaction. The result of that is you see an increase in the rate of the reaction, again, because you kind of lowered the hill that everybody's got to climb to get to the other side. So now you've allowed a lot more reactants to get up and over this to the other side because it's a much smaller hill. Any questions on that there? Catalysts a lot of times in reactions are kind of written a lot of times on top of the arrow, you know, maybe something like a platinum metal or maybe H+, which is an acid catalyst. So sometimes things are just kind of written on those arrows. So let's talk a little about equilibrium. Equilibrium is a process, as I mentioned, when we have a reversible reaction where the rates of that forward direction and that reverse direction will eventually be equal to each other. And this is always happening in terms of equilibrium at phase changes. So the process of taking something from solid to liquid, or liquid back to solid, liquid to gas, or gas back to liquid, whatever it may be. Those are very common places where we do see equilibrium occur. And remember, for example, at the normal boiling point, say of water at 100 degrees Celsius, you have basically both phases in equilibrium with each other. So you got kind of like steam. You also got some liquid water. Same thing at 0 degrees Celsius, the normal freezing point or melting point of water. You got like ice crystals. So you got some solid there, you got some liquid there. Not really till you get above or below those sort of temperatures that you fully sort of transition. And again, that equilibrium process is always occurring. Even at the surface of any liquid, you got some liquid molecules jumping out of the liquid phase into the gas. You got some gas molecules coming back the other way. Chemical equilibrium is a dynamic state where the concentration of reactions and products do remain the same. As I mentioned earlier, that is a result of that forward and reverse direction rate basically equaling each other. Now, when we look at something that has reached chemical equilibrium, say you look at your test tube or your beaker, or wherever you may do a reaction, it may look to you like there's not much going on. It just may look like the reaction is done, but there is a lot of activity that's actually happening on the microscopic level. You constantly have guys going from reactants to products, products back to reactants. So there is a lot of activities actually happening, even though visually, if you were to look at it on sort of the really macroscopic level, it may look very static, like it's over, nothing's happening. But if you were able to really kind of zoom in and see what's happening, there's a lot of activity to maintain that system at equilibrium. So sometimes people look at something and go, well, it's over, not much is happening. But again, there's a lot happening, especially in these equilibrium type reactions where visually you may not be able to visually kind of see it happening, but there's a lot of activity that's basically happening. So when we look at reaction and something that reaches equilibrium, in a lot of cases, if this is sort of our products, if you will, our reverse reaction, this is our forward reaction, our reactants. Pretty much when we start, it's all about reactants, and really the forward direction predominates in this reaction, especially if we have no products to begin with. So if we have no products, pretty much all we have is reactants. It's going to all start going to the product side. That's basically going to predominate. At some point, we're going to be making some of our products here, and we're going to build up enough of those products that they will start coming back the other way. And that's what we see happening here. So we see sort of a decline. And then basically what will happen is at that point where everybody levels out, they don't necessarily have to be the same concentration, but this is actually the rates here, where those rates of the forward reaction and the reverse reaction equal each other. That is when chemical equilibrium has basically been reached. And if we were to just look at a thing of our, say, reactants versus our products, and we were to kind of make a graph like that, and this is time. Again, at the very beginning, in a lot of cases, it's all about reactants. But as this starts to come down, we'll start to see some products being made. And at some point, they will both, if I could draw a straight line, would level out there. Imagine those are straight-ish, not going up at too much. We'll try to straighten them out a little bit. There you go. So at some point, they will basically level out their concentrations, and that is when chemical equilibrium has been reached. Again, past that line is coming straight down. These concentrations, again, if these were perfectly drawn straight lines, they're not really changing. So they have reached equilibrium, and that's because the rate of the forward reaction and the reverse reaction have equaled each other. And none of those concentrations are going to really change unless you do something to really kind of screw it up and change it. Questions on that there? As you can see in this graph, again, it doesn't mean that you have the same concentration of products versus reactants, but definitely when those concentrations basically lock into place and really aren't changing, that is when equilibrium has been reached. So let's take a look at this reaction here. Water plus carbon monoxide makes some H2 and CO2. And if we have this system at equilibrium and we decide to add some more H2O to this, how does everybody's concentration change when we do this? So what will happen when I add this H2O? I am now going to add this H2O, and that should really kick off the forward reaction or the reverse reaction in this case. It should kick off the forward reaction because now we have a lot more reactants, which means they can react with each other a lot quicker. And that's really going to kick off the reaction heading in the forward direction. The result of that is, in terms of the H2 concentration, it should go up, right? Because we should be making more products. The CO2's concentration should also go up because we're heading in that direction. We're making more products. How about the CO concentration? It should go down, right? Because the only way to make products is to use our reactants. So we should see its concentration basically come down. Now, the water that we added, we'll see kind of a slightly different sort of pattern with it. With the water, we will first see it go up, and that is because you added it. So clearly it's going to go up. But once the forward reaction starts, we then should see the water start to come back down, right? As it's reacting with the other reactant that's there. So because you added it, it's going to artificially kind of go up high, but then it should start coming back down. And depending on how much you added, it may actually end up higher than it started only because you added it. But you should definitely see it go up, but then start to see it go down as it's reacting in the forward direction. Any questions on that there? So if we look at this one here, but decide instead of the water here to add our H2, we could kind of think about the same thing here. If we add some H2 here, that should increase the amount of products, which actually should have the reverse reaction basically kick off here. So with that extra H2 being added, that's going to allow those products really to kind of come together and kick off. And that will cause the reverse reaction basically to take place. And the result of that is the CO2's concentration should go down as it's making some more reactants, as it's heading in the opposite direction. The amount of H2O here should go up, and also the CO should go up as the reverse reaction here is going to be predominant and we're making more reactants. And again, here with the H2, we will see something similar to what we saw with the water. It would obviously artificially sort of go up because you added it, but then as it starts reacting with the CO2, it should start to head back down in the opposite direction. Any questions on that there? All right, so let's talk a little bit about a relationship that we have with these type of reactions, and that is the equilibrium constant. So the equilibrium constant is abbreviated with a capital K. It is also Chem 1B, what the letter that class is brought to you by. You will learn about every single equilibrium if you take 1B that there is. But the equilibrium constant is essentially the concentration of the products divided by the concentration of the reactants. And a reminder that if you see these little brackets, that means concentration. And really that means molarity, which is our moles per liter in most cases. Now, when we do write this, there is a relationship that if you take the concentration of your products to your reactants, it will give you this constant value, which is why it's called the equilibrium constant. The equilibrium constant is a constant value for a particular reaction at a specific temperature. So temperature is the only thing that can actually change the value of the equilibrium constant. Nothing else will change it. So as long as you don't change the temperature, you should get a constant value no matter what happens for that particular reaction. So if we look at this reaction here, the equilibrium constant would be the concentration of C, and we do take the balance coefficient as the exponent, which is an important part when we do write the equilibrium constant, divided by our concentration of our reactants, again, taking the coefficients as the exponents. This is what is referred to as sometimes the Kc value. C meaning concentration. There's all kinds of K values, Kc, Kp, Kw, Ksp, Kf, Ka, Kb, you know, you could keep going on and on. But they're all basically the same thing. They're all basically products over reactants. For example, if these were all gases, let's just say, for example, if these were all gases here. When we deal with gases, we oftentimes deal with pressures rather than, say, concentrations. So you could write an equilibrium constant involving pressures, and it works the exact same way. The K here would be the partial pressure of C to the C times the partial pressure of D to the D divided by the partial pressure of A to the A and partial pressure of B to the B. These all use pressures, so this is sometimes what is referred to as the Kp value, P for pressures. Typically speaking, if you're doing anything with the equilibrium constant and it is pressures, atmospheres is the units that you want to make sure that you are in. So usually atmospheres is what you want to use. You can actually put values into here if you know either the equilibrium pressures or the equilibrium concentrations. They do have to be equilibrium concentrations or pressures in order to go into here to get a number. You can't use initials. You have to use the actual equilibrium values. One nice thing about K is it is frankly just a number, no units. So it is just a number. And the number tells us a couple of things. Is this a number? No units. And if the K value is large, that means when we reach equilibrium, we mainly have products. So if you think about just mathematically, in order to get a large number, you need a bigger number up on top than the bottom. So you should have more products than reactants. And if you have a small value of K, that means when you reach equilibrium, you mainly have reactants. And again, math-wise, that would mean you have more on the bottom number than the top number there to do that. What is considered a large value versus a small value? Pretty much it is the large number of 1 is considered a large value. So anything 1 and above is considered a large value of K. Anything less than 1 is considered a small value of K. And there is extreme degrees of differences in there. So for example, you could have a really extreme sort of value, like a K value that goes to the minus 42, which is super small, and which means it's mainly reactants, it ain't going anywhere. Or you could have a really large value of K, that's like to the positive 54 or something like that, which is a super large value of K. And you could have anywhere in between, you know, obviously those type of numbers. So if you have a really, really large value of K, it's almost safe to assume that the reaction is pretty much a one-way street, even though technically it will still come back the other way, not very much, but it'll still come back. And if you have a really, really small value of K, it's pretty safe to assume that it's going to just hang out there on the reactant side. Not much is going to the products. It's just going to kind of stay there, but a little bit of it will go. Now, KP and KC usually, in most cases, do not give you the exact same numerical value, but they do tell you the same thing. Again, if you have a large value of KC, you would have a large value of KP usually, and vice versa, obviously, if you had a small value. Any questions on that there? All right, so if we look at this reaction here, we would take our products, which in this case is the concentration of NH3. We would square it because of the coefficient, divided by the concentration of N2 and the concentration of H2, which would also be cubed. And once again, this would be our Kc value. And in this case, they're all gases, so we could write a Kp, which would look very similar, except that it would be the partial pressure of NH3 squared, divided by the partial pressure of N2 times the partial pressure of H2, and that would be cubed in that case. So again, you could use pressures or concentrations. It really does work the same way. Usually concentration should be molarity, obviously, and usually pressures should be atmospheres is the most common sort of unit there. As I mentioned, and something that sometimes people have a really hard time understanding is that the value of K is a constant value at a particular temperature, and that's regardless of how much you start with. So for example, if we were looking at that reaction, like a reaction like A plus B goes to C plus D, you could do this experiment at 25 degrees Celsius one time where you start with just A and B, no C and D. You would get a K value for this reaction. You then could do it actually with just C and D and no A and B, so all products, no reactants, and you would get the same K value. You could start with a little bit of A, B, C, and D, it doesn't really matter, and you would get the same K value as long as you did not change the temperature. Now, if you then did this reaction, say, at 40 degrees Celsius, and you started with all reactants, you would get a K value that would be different than the one you got for 25 degrees. If you did it with all products, it would be a K value that's the same K value at 40 degrees, but different than 25. And if you did it with a little bit of everybody, again, you would get the same K value at 40 degrees in all those situations. So as long as you don't change the temperature, you could do the same experiment. You can start with multiple different amounts of everybody. It will always come to rest at the same proportion of products to reactants. So I explain it this way. It doesn't really matter what you start with, but there's many different ways you could get to the same ratio, right? So if I wanted like the number 2 to be my ending part, I could get 2 by taking 2 divided by 1 gives me 2. I could get to 2 by 4 divided by 2 gives me 2. I could get to 2 by 8 divided by 4 gives me the 2. That's all different numbers. The end result is the same proportion. It's still 2. And that's the same thing that happens in an equilibrium reaction. It really doesn't matter how much you start with of anybody. It will always come to rest when that rate of the forward reaction and the reverse reaction come equal to each other with the same proportion of reactants to products. Again, as long as you don't change the temperature. Any questions on that? Now, you could, if you were to compare, again, the K value at 25 degrees at 3 different experiments, they would all be the same. 40 degrees, they would all be the same at 40 degrees, but comparing 25 to 40, they would be different values. Any questions on that? Yeah. All right, so here, if we look at this reaction here, we want to write our equilibrium constant. Once again, we're going to take our products, which is our H plus and our acetate in this case, divided by our reactant. And again, obviously, none of these other guys would be the correct one. All right, so if we were to, for this reaction, we want to calculate the value of the equilibrium constant. The first thing that we would want to do is write our expression, which would be, again, our products, which is NO2. And again, we need to square it because of the coefficient. We would divide it by the concentration of N2O4. And in this particular case, they gave us the equilibrium concentrations. So at that point, all we have to do is plug it in. So our 0.060 squared divided by our 0.055. And I'm going to trust her math, hopefully 0.065. I don't know, maybe I shouldn't trust it. We'll see. 0.06 squared divided by 0.05. All right, any questions on that there? Yeah. Now, what we've been looking at so far was sometimes referred to as homogeneous equilibria, and homogeneous equilibria is much like homogeneous mixture, is basically the same. That means that everybody's in the same phase. So everybody here would be in the same phase. And again, if we were to write our equilibrium constant, say for the last one, it'd be H plus Cn minus divided by HCN. And everybody here is aqueous. Everybody here is gas, and that is what is meant by homogeneous equilibrium. Everybody's in the same phase. That is not always the case. Sometimes you do have some things that are sort of mixed over in terms of different phases. So this is what is referred to as heterogeneous equilibrium. And here we have some mixtures of some different phases. And when we talk about the equilibrium constant in the expression, there are 2 things that we really do not include in those expressions. And those 2 things that we do not include is anything that's a solid or a pure liquid. So anything that has a solid next to it, or an S, anything that has an L next to it, is not included in the equilibrium expression. And that's because they're really not participating much in the reaction. The easiest one to visualize is probably the solid. If we think of the solid like you drop a rock into some water, it's just going to sit there on the bottom, not do much, right? It's not going to really participate very much in it. In order for a solid to participate, it has to dissolve, which means it's no longer a solid. It would be an aqueous ion and floating around and able to participate. Things that are pure liquids, they have pretty much a constant concentration. They don't change very much. So those 2 things do not get included, which means there are actually 2 things that are included. So the 2 that are included in the equilibrium constant expression is anything that is aqueous, because it's floating around ready to go and react, and anything that's a gas, because it's basically flying around and ready to react. So only things that are gases and aqueous are included in the equilibrium expression. So why don't you take a moment and write the equilibrium expression for each of these? You could just do the Kc values for each of them and see what you come up with. This one here will go with our products, which is our KCl, which we should not include, right? Because that is a solid. So we do not want to include it. So we will include this guy, which is a concentration of O2 cubed. And on our reactant side, that is also a solid, so we would not include it. And that would be our equilibrium expression in this case. It would actually just be the O2 is the only thing really participating in this case. Now, if we come here, our second guy, it would be our H2. Again, we would square it because of the coefficient. That would be times O2, and the coefficient here is 1, so we don't have to worry about it. That is a liquid, so that would not be included either. Any questions on those? Now, if you happen to have, for example, I don't know, maybe like a liquid or a solid on this side, but something that's, say, aqueous maybe on that side, if you were to write the K, it would be 1 over your reactants. So if you happen to have just something on the reactant side only, that should be included, but nothing on the product side, you just do 1 over the reactant side and you'd be okay. Any questions on heterogeneous? So solids, liquids don't include. Aqueous gas does get included because, again, they are basically moving around and basically actively participating. I guess you could think of it that way. And that's what we see here. All right, so we want to determine the equilibrium expression here. Once again, it would be our products times our times both of the products there. We do want to square it. When we come to our reactant side, again, we have a solid. So that should be that guy right there. Yeah. Any questions on equilibrium constants here, expressions? All right, the next thing we're going to talk about is what happens when we do have a system that is at equilibrium and we frankly kind of screw it up. And the system itself will want to readjust to kind of fix that. And that is what is known as Le Chatelier's principle. So let us talk about that officially here. So if we have a change that's imposed at a system that's in equilibrium, the system itself will basically change to fix that. So basically, if you have a reaction that has reached equilibrium, like equilibrium position number 1, then you do something to it, like you add some type of stress to it. What's going to happen is it's frankly going to screw up the rate of the forward reaction and reverse reaction from being equal to each other. But what's going to happen is this reaction is going to want to get back to equilibrium. And there's really kind of 3 things that it could do to get back to equilibrium. So if you add a stress, you'll no longer have that rate of the forward equaling the rate of the reverse. It will try to get back there by shifting to the left. And when we shift to the left, that means it will make more reactants, which is left-hand side of the arrow. It could shift to the right, which means it will make more products. And there is some situations where even though you do something to it, the reaction itself will not change. So there'll be kind of no change that can occur. So that is a possibility. So what are some of the things that we could do to this to really mess it up? We could do something with the concentration. We could do something with pressure and volume if we're dealing with sort of gases. We could also do something with temperature, and we could do something like add a catalyst. So these are a few things that we could do to a system to really stress it out, and it will mess up that equilibrium. It will want to adjust one way or the other. And eventually this guy will return back to a state of equilibrium. So it'll come back to like a second sort of state of equilibrium where, again, the forward reaction and reverse reaction will equal each other. So we're going to talk about each of these and sort of how the system will basically change based on what you do to it. So let's start with concentration first, I think. So concentration, there's really kind of two things you could do to it. You can either add more or you could remove. Those are basically your two options. And when we add more, it will always shift away from the side you added it to. So AA, add away, it's going to go away from whatever side. You add reactants, it will go to the product side. You add products, it will go to the reactant side. This can go away. When you remove it, it will go to the side you removed from. So I sometimes think of removing as like you create a hole in that side. So what happens is it will go towards that side to like fill the hole back up. And that's what basically happens when you remove something. So very simple sort of explanation of adding is like you probably did in that experiment. You just simply grab a bottle that has something in it that's the same as in the reaction, and you dump it into your flask or your beaker, and you will basically be adding it. Removing is a little bit different. To remove something from, say, an aqueous solution, you need to add something perhaps that will react with something in that reaction and make a solid is one way you could remove it. So to remove something, you could add something that will make a solid. Again, a solid would not be included in the equilibrium. So that'd be like essentially reaching in there and taking that ion out of the solution that's floating around as it comes down as a solid. That is obviously something that you could kind of see. Another way that you can remove something from a solution is if you have hydroxide, OH minus or H plus or H3O plus, if you add an acid or base to it, you can make water. Now, water is a little bit harder to see because it's water, so you can't really see, ooh, I made more water or anything like that. But when you do make water, that would be like removing OH minus if that was in the equilibrium, or if there's H plus or H3O plus, it would be like taking it out of the equilibrium. So when we're dealing with something like concentration, you know, if we had, say, this system that's at equilibrium with the classic stick figures here, this is going to be my reactant side. This is going to be my product side. And this guy decides we're going to hop somebody up onto that side. And if somebody gets on that side, this is the situation that's going to develop. This is not advanced stick figures as there's no faces. But here that's going to mess up equilibrium. And clearly in this case, we need to put more people on the left-hand side, right? Opposite of where we added to fix this. So to fix this, we're going to shift away from the side we added it to. And again, here we will return back to equilibrium, basically. And if we were to take something like this, and again, if this is our reactant side or product side, and this guy on this side decides I'm just going to hop off, no problem, just hop right off of that thing. This is going to happen. Right. So in this case, we actually need to put more people to the side where it got hopped off, right? And we removed it, and it would shift that way. Once again, returning this guy basically to equilibrium. Any questions on that there? So again, I think of removing as like a hole to fill, so it goes towards that hole, and adding goes away from AA. Add away is a good way to remember that. So again, there really is, when we think about Le Chatelier's principle, sometimes we go shift to the left, shift to the right. There's obviously no right-hand side or left-hand side in like the beaker. Everybody's floating around in there. So we're thinking about the reaction that we're looking at as right-hand side, left-hand side, more products or reactants. Any questions on that there? So the next thing that we could look at is pressure and volume. And they sort of all are tied together, especially obviously if we're dealing with gases. And when we dealt with gases and we think about those gas laws, our good friend Boyle had a relationship about pressure and volume. As the pressure goes up, what happens to the volume? It goes down, opposite, right? And as the pressure goes down, the volume goes up. So that is sort of what you want to think about when you think about pressure and volume in Le Chatelier's principle. If the pressure goes up, that is a result of the volume going down. So really the change that's happening here is we see the pressure start to rise. So we kind of want to bring it back down. At this point, though, we have a much smaller volume. If I put more gas molecules in a small volume, the pressure should start to go up, right? Which is not good. We actually want it to come back down. So in that smaller volume, we actually would need less gas molecules. So it will shift to whichever side has the least number of gas molecules. And that obviously is reaction dependent as to which side has the most gas molecules. You shouldn't overthink it either. It's just simply whoever has a G next to it, add up the coefficients on each side, and that's how many gas molecules you have. Opposite is true. If the pressure starts to drop, that means the volume is going to start to increase. So pressure coming down, we want to bring it back up. So to do that, we're going to need more gas molecules in that larger volume. So it will shift to the side with the most gas molecules. So let's say we had this reaction here, 2A plus B goes to 4C. All right, so will it shift to the right, to the left, or no change if I add more C, I remove B, I increase the pressure, I increase the volume. So take a moment there. Which way will it shift in each of these cases? Okay, let's take a look. So here we're going to add more C. So that's a product that will kick off the reverse reaction happening. And that's going to mean that it is going to shift away from it. Here we're removing B, which means it will create like a hole on that side. Essentially, you have more products and reactants at that point. That also will shift towards the side we removed it from to try to fill that hole. When we increase the pressure, that means that the volume is getting smaller. So I personally look at volume in this situation, small volume, less gas molecules. So when we look at this reaction, that is 2 and 1 is 3 gas molecules on the left. And this side has 4 gas molecules, which means it should go to the left in this case. Lastly, here we're going to increase the volume. That means the pressure actually will come down in this case. And again, looking at just the volume, bigger volume, more gas molecules, which means he actually should shift to the right in this case. Any questions on any of those there? The next thing that we're going to deal with in terms of Le Chatelier's principle is actually temperature. And temperature, obviously, you can either raise the temperature or lower the temperature. The good news is temperature really does work like concentration. So temperature basically does the same thing as concentration, which means that if you increase the temperature, it will shift away. And if you decrease the temperature, it will shift towards it. So what determines sort of which way that shift would be is really the type of reaction that you're going to be dealing with. So there's either an exothermic reaction or an endothermic reaction. And in an exothermic reaction, heat and energy is released. And when we think about exothermic, we think of heat as being a product. So we think of heat and energy as being on the product side. And that is different than endothermic, where heat and energy is absorbed. And when we think about an endothermic reaction, the heat or energy is considered to be more of a reactant. So depending on sort of what type of reaction you have, If it's exothermic, you increase the temperature, it will go to the left. And if it's exothermic, you decrease the temperature, it will go to the right, and vice versa for endothermic. Probably most commonly, this is how you determine exothermic or endothermic. You're given a delta H value for the reaction is most commonly how that is done. Remember, again, doesn't really matter in terms of this application what the number is, but it's really just the sign that's important here. So if you again have a negative value for delta H, it's going to be exothermic. And you can think of heat and energy as a product. And if you have a positive sign for delta H, that means the reaction is endothermic, and you can think of heat and energy as a reactant. Any questions on that there? Lastly here, a catalyst. Again, as we talked about earlier, is not a product, is not a reactant. It is there simply to make the reaction occur faster. It will actually have no change on the equilibrium. A couple other ways that you can kind of get a no change situation is if you add to something like a noble gas, which is chemically inert, doesn't really react with things, that would get you a no change. And then also, if you think about sort of the gas situation where you're counting up gas molecules on each side of the arrow, if you end up with a tie, like 3 on each side or something like that, there obviously would not be a side that's more or less gas molecules. So that would be a no change situation if you end up with kind of a tie on both sides of the arrow in terms of numbers of gas molecules, and you're doing something with pressure and volume. Any questions on that there? All right, let's take a look at one more here. So let's do N2 plus H2 and H3. Let's go delta H equals plus 325. Clearly not the right number, just made it up. All right, we're going to shift to the left, to the right, or no change. If we do these things, add H2, decrease the volume, decrease the temperature, decrease the pressure, remove N2, add a catalyst, increase the temperature. All right, take a moment there, see what happens in each of these cases. All right, let's take a look. So we're going to add some H2. So H2 is a reactant, which means it will shift away from it, which means it will kick off that forward direction and head in that way. When we lower the volume, that means our pressure is increasing. That also means we have a much smaller volume, which means we need less gas molecules. And in this case, we got 4 gas molecules, looks like over here, and we have 2 over here. So we need less gas molecules, which means it will shift to the right in this case. If we decrease the temperature, in this case, this is a positive value for delta H, which means it's endothermic, this reaction, which means heat and energy is considered a reactant. So if we decrease the temperatures, like removing reactants, puts a hole on that side. So we got to fill that hole and go towards it, and it would shift to the left there. In the case of decreasing the pressure, that means that we would be increasing the volume. So once again, we have a much larger volume. We need to put more gas molecules in there. And in this case, it is to the left that will do that. Lastly, again here, removing N2. So N2 is a reactant. So to remove our reactant, we're putting a hole on that side. So we got to go fill it. So we're going to put an arrow heading in that direction. We're going to add a catalyst, which will just get us there quicker, but no change will occur. And lastly here, if we increase the temperature, that in this case would be like increasing our reactants, which should kick off that forward direction. Any question on Le Chatelier's principle there? Yeah. So we just talked about that, affect the concentration, affect the volume, increasing the system. Again, that exothermic, endothermic, we could think of exothermic heat and energy again as being a product, endothermic, it being a reactant. And remember, again, that temperature change is really the only thing that will affect the actual value of the equilibrium constant. From one temperature to the next, you'll get a different value. All right, so let's take a look at this one here. Consider this reaction. How many of the following would lead to a shift in equilibrium towards the reactants? So in this case, we're looking for something to shift it that way. So let's take a look at each of these, see which three of them are the right one here. If we remove CO, which is a product, it actually will shift to the right, which means that's not good. If we add some O2, it will shift away, which means it should shift to the left, so that's good. If we remove CO2, which is a reactant, has a hole on that side, shouldn't make it shift that way, so that will do it. And increasing the pressure in this case by decreasing the volume. So smaller volume, less gas molecules. So in this case, we have 2, and we have 2 and 1 is 3 gas molecules. So that would cause it to shift there to the left. So it looks like those 3 are the ones that actually will cause it to go to the left. Any questions on that one there? All right, let's take a look at one more here, I think. In this case, this is an endothermic reaction. We're looking for whichever will cause hydrogen gas to be produced. How many would decrease the amount of hydrogen gas? I'm sorry. So to decrease the amount of hydrogen gas, we actually want to shift it away from hydrogen, which means we want it to go to the left in this case to have less hydrogen. Let's take a look at higher water is added. So again, water in this case is a reactant, which means it will shift away, which will go to the right. So that's not good. The volume of the container is doubled. So larger volume, we need more gas molecules. So that's going to give us 2 gas molecules here and 4 here. So that's going to cause it to shift to the right, which will not do it for us. CH4 is removed. So that is removed, which is a reactant. So that's going to cause it to shift towards it. So that will do it. And lastly, the temperatures increase. So this is endothermic, which means heat would be over here. And if we increase the temperature, it would cause it to shift away. So that would not do it. So number 3 there looks like what would cause it to make less H2 in this case. By the way, here, water is included in the equilibrium, right? As it is a gas in this case. So if you have water in the liquid form, not included, but water in the gas form is, as it's a gas molecule and it's flying around, causing collisions. Any questions on Le Chatelier's principle there? All right, so the value of K, again, really large value will go to the right. Essentially, it is going to make the reaction go to completion. And obviously, as we talked about, if you had a smaller value of K, you're pretty much going to hang out on the reactant side, not really going to make a lot of products. All right. And that's what we see here, large value to the right and left small value K. All right, so let's take a little bit about using the equilibrium expression to solve for maybe a missing equilibrium concentration. Clearly, we could just stick our values in there and get the equilibrium constant. So in this case, if we were to take this reaction, K is equal to our HI. And again, we would square it because of the coefficient, divided by the concentration of H2 and the concentration of I2, and this equals 50. In this particular case, we're looking for the equilibrium concentration of H2. So if we rearrange this, H2 would equal HI squared, divided by 50, which is our equilibrium constant, and our I2. So we do have the values of everybody else, so we can put them in there. This is going to be 5 times 10 to the minus 1 squared, divided by 50, and that will give us 1.5 times 10 to the minus 2. And that should give us our equilibrium concentration there of H2 in this case, which would be 3.3 times 10 to the minus 1. Again, it has to be equilibrium constants, concentrations to some form. And again, use it like we just did here to solve for maybe a missing concentration if you know everybody else. You obviously can, like we did earlier, just stick it in there and get the actual value of the equilibrium constant. Any questions on that one there? All right, so to finish up here, just briefly, and maybe we'll do a little bit more next time, but sometimes you're not given the actual equilibrium concentrations, but you are given like the initial concentrations. And we could do a calculation that allows us to use the equilibrium constant to figure out the actual equilibrium concentrations. So your book talks about a specific type of equilibrium expression, which is known as KSP. And KSP stands for the solubility product. It's just like KC, KP, KA, KB. It is the equilibrium constant for things that are technically insoluble. So if you remember those solubility rules, there's some ionic compounds, right? If you put them together, you get a solid that's formed. And that's really what this is for. This is sort of an equilibrium constant for things that are technically insoluble. So if you just took something like, say, silver chloride, for example, that based on solubility rules is insoluble. And even though silver chloride is insoluble and things are insoluble, there is a certain degree of it that will actually break apart into ions, even though it's maybe really, really small. And in this case, we can write an equilibrium expression for this, known as the KSP, which would be a products times each product divided by reactants. And once again here, we would not include this reactant as it is a solid. And most KSP guys are pretty much that deal. They're solid on the reactant side and ions on the other side. So usually if you write a KSP expression, unlike a traditional equilibrium expression, you basically have just your products in the reaction. Now, we can actually do a calculation to figure out, if all we know is we have this guy is going to break apart, what are we going to end up with in terms of air base concentration? And to do this, this is what is sometimes referred to as an ICE table. And an ICE table stands for initial, change, and equilibrium. And for the change part, we usually will use a letter, and the common letter is X, is what we use to represent the change that's going to occur. So we can calculate something like what the concentration of everybody would be at equilibrium by doing this type of calculation. And let's take a look at, say, this one here to see how we would do this. So in this particular case, you don't actually need to do a nice table, but let's take a look at how it would work. So we're going to have our lead 2 chloride, and it's going to break apart into a lead 2 ion and 2 chloride ions when that breaks apart. That will give us our KSP, our equilibrium expression of lead times Cl minus, and once again, we do need to square it because of the 2 that is there. Now, in a table like this, if you come across anything that's a solid or a liquid, you really should ignore it because frankly, it's not involved in equilibrium. So initially here, we aren't told anything about these guys. So it is safe to assume that you have 0 of each of these guys. And again, I'm not going to put anything on the reactant side because that's a solid. If it wasn't a solid, you might have an actual concentration and you would put a number there if it was given to you. Now, in this reaction, it is also safe to assume that it's going to probably head towards the product side. That means as this reaction goes on, the amount of reactants should start to decrease and the amount of products should actually start to increase. And we represent that in a nice table with minuses and pluses. So the reactant side is typically minuses and the product side are typically pluses. And we represent the change with X. So the change here would be plus X and plus 2X. Now you do have to take the 2 into account here because of the stoichiometry. That takes care of the mole to mole relationship for you and everything's good. At this point, we could get to the equilibrium line by just simply bringing everybody down. And we end up with this. Now, in a traditional ice sort of problem, you will be given a lot of times the K value. And normally what you would do at this point is stick these guys into here and basically solve for X. And that would be the X that you see in each of these tables. In this case, we're actually looking for what the KSP value is. So we're going to do the same thing. We would take our KSP and we would put our X in place for the lead 2. And for the chloride, it is 2X, and we still need to square it. Now, in this particular problem, they were nice enough to tell us that the lead at equilibrium is this number. And if we look at our ice table, lead at equilibrium equals X, which is the same X as this X and every other X that you would find in that table. So we actually already know what X is. So in this case, we could take 1.6 times 10 to the minus 2 times 2 times 1.6 times 10 to the minus 2. We still need to square it at the end. And if we do that, we will get 2 times 1.6 to the minus 2 squared times 1.6 to the minus 2 gets us a, in this case, KSP value, go this way, of 1.6 times 10 to the minus 5. So as you can see here, we could use an ice table to make sure that you actually multiply it by 2 and also square, which is a very common mistake people make sometimes. They go, I already multiplied by 2, what still squared and all that kind of stuff. So it sometimes can be helpful. Other variation of this is you can use an ice table to figure out what the equilibrium concentrations of everybody would be by solving for X. Any questions on that? And we'll